All right, everyone. We're going to go into the first. Thank you all for coming today. Hope you're enjoying the food. Thanks to Judisha for ordering it. Today we have Arha, who's presenting for us on the traveling salesman problem and space filter curves. This is going to be more of a tutorial style talk, so hopefully it's accessible not only to people in optimization control, but to those who don't do that. So a little bit about Arha. He is a second year in the economics group. He before coming to Penn, he was at UPenn, where he did his master's. So yeah, we're very excited to have him. So please give me your attention and welcome him.
Thank you so much, Vasan. So this talk is going to be outside of my research, something which I found really interesting when I took the course Theory of Probability. So most of the content is from Professor Santosh's book on Theory of Probability. We'll see how this goes. So I'm going to talk about the widely studied NP-hard problem in computer science, which is the traveling salesman problem. And we'll see how a mathematical tool called the space filling curves will be used as a heuristic to solve this problem. Right, I'll start with a little bit of Philadelphia connection. So the first food delivery program in America was started in Philadelphia way back in 1954. But this was nothing close to compared to like the Uber Eats or Grubhub, which we use today. It was the target audience, the target customer was elderly people and people who are prone to illness, who could not come out of their house regularly to get groceries and food. So a non-profit organization created a system where they could deliver food to these people on a daily basis. So the problem looks like this. You have so this was implemented in Georgia, Atlanta way back in 1982. So you have a set of home locations where these people reside, and you have to deliver food to these people in minimal time, right? You don't want to spend a lot of time in delivery. So the problem is as simple as that. Let's say if these are the locations of the home on a map, and the problem is you have to go to visit all these homes in minimal time. But there are more things to this in the sense that the first problem is the number of clients keep changing frequently. So some people subscribe to this program, they opt out of this program. So from the data in 1982, the number of clients varied from 159 to 358. So you have to alter these routes on a weekly basis. So you can't really spend a lot of time solving this optimization problem. Another thing is this was run by a non-profit organization. So it is very hard to get a lot of resources. You can't put a lot of money in hiring a lot of people. And this was back in 1982. So computers weren't a really big thing then. So you probably have like 1 or 2 people maintaining something so that you tell the drivers, okay, this is the route you have for today, which is optimal in some sense. So because of these problems, you would definitely need an efficient routing algorithm. Just to make it clear that this is very hard, let's say you have n locations. There are like n homes on this map. The total possible number of permutations is going to be n factorial. And if you increase n, it is easily going to blow up. So you can't just search through all the n factorial permutations to compute the length of each of the route to find the best route. So you have to have some kind of a clever way to find this route as quick as possible. I'll start up with a very simple idea. Let's boil this down to a one-dimensional case. Let's say you have a set of numbers on the line, and you have to visit these numbers optimally. It's very simple. You just sort these numbers, and you go from left to right. So you start from the leftmost location, and then there's traverse in order. But obviously, we are not going to have locations on a one-dimensional space. It's going to be at least on a two-dimensional space, right? But what does it mean to say sorting on this this two-dimensional space? It's not like kind of well-defined. So how do you sort these points? But the idea here is, if we can have a very efficient way to map these two-dimensional points to one dimension, sort it in one dimension, and then map it back to 2D, then probably that could be a way of getting a close to optimal route. So this is like the basic idea. Map the 2D points to 1D, sort it in 1D, and then map it back to the 2D map. But now, as always, the devil is in the details. So what is this map going to look like? We want some kind of a nice mapping so that you can perform this mapping function efficiently. Very natural question to ask us, will this mapping be continuous? Is it easy to compute and stuff like that? Just to illustrate this idea, let's say you start from this point on 2D, and the mapping of this point is going to be the corresponding point in 1D. And as the vehicle moves in 1D, this is how it moves in 2D as well. So you are mapping the corresponding points to 1D, and as you move from left to right in 1D, this is how it's going to move in 2D. This is like the big picture. Any questions on this idea, how this is kind of formulated? Now, to make this more formal, let's see how you are able to construct this mapping. So this mapping is basically going to be the space filling curve. I will explain now how we will construct this curve. To make things algebraically more simple, I'll just concentrate on a unit square. So this square is from 0 to 1 and 0 to 1 on x and y axis, and the unit interval is going to be from 0 to 1. And your objective is going to take a number from the unit interval and map it to this unit square. Let's say you go from left to right in the unit interval. I'm going to divide the unit interval into 4 equal subintervals at the first stage. And similarly, I'm going to divide the square into 4 equal subsquares. So you start from left. This interval is going to map to the first subsquare. And as you go towards the right, the second interval is going to map to the second subsquare, and so on. This is just the first stage of construction. Now, in the second stage, you're going to further divide each of the subsquares into 4 more subsquares. For example, if you take the third one, I'm going to further divide it similarly. And the interval from the third subinterval, which is from 1/2 to 3/4, is going to further get divided into these 4 subintervals, and you do the mapping in a similar fashion. So at stage 2, your curve is going to look something like this, because you're going to divide each of the subsquares into 4 more subsquares, and the resolution is going to be like by 16, because you're dividing each of the squares into 4 more squares. At stage 3, it's going to look a little bit more wrinkly. And as you increase n, it becomes more and more dense. Right? Yes. Question.
So you have 4 more squares.
Yes.
So I don't see where the squares are.
So do you understand the first construction, how we are doing? Okay, so this is the unit interval, and you go from left to right. You're dividing the unit interval into 4 equal subintervals. So this is going to be 0, 1/4, 1/2, 3/4, and 1. And the subinterval, the first subinterval from 0 to 1/4 is going to get mapped to the first subsquare here. So this subsquare is going to be 0 to half here and 0 to half here. And you go sequentially. So this is going to be 1/2 to 1, and then this is going to be 1/2 to 1, and so on. Now at the second stage, you're going to further divide each of these subsquares into 4 more subsquares. And this is just an example for the third subsquare. So the red line is going to denote a path when you move in the interval from 0 to 1. So as you move from 0 to 1, you're going to trace this path, 1, 2, 3, 4. Yeah. Now at stage 2, you're going to further divide the subsquares. So you're kind of increasing the resolution. So now when you move from 0 to 1 here, you're going to trace this path from 1 till 16. So as you increase n, you can see the unit square is kind of becoming more dense, in the sense that the path is covering essentially all the points in the unit square. So as n tends to infinity, you're kind of filling the unit square. That's why it's called like a space filling curve. And just to observe, you can represent any number in the unit interval using this quaternary representation. So each Tn is a number between 0, 1, 2, or 3. And any number in the unit interval can be represented like this. Just as a sanity check, if you make all the Tn equal to 0, theta is going to be 0. And if you make all the Tn equal to 3, theta is going to be 1. And as you make each of the Tn 0, 1, 2, or 3, you cover entirely all the real numbers in the unit interval. And another observation is this map is a surjection, meaning that given any point in the unit square, you will be able to get a point in the unit interval using this mapping. The intuition is given any point in the unit square, let's say given let's say you're given a point somewhere here, then this definitely has a nested sequence of subsquares which converge to that point just by this construction. So you can always go from the point in the 2D plane back to the unit interval. Tn or like similar to binary digits, but they have 4 possible values: 0, 1, 2, or 3. Any questions in how we are constructing this curve? Right. Sorry? No, so theta is living on the one-dimensional space.
Oh, okay.
Right. Yeah. Now let's go into how this algorithm is actually used. So let's say you're able to compute this map efficiently, and this is just like a simple way of getting this curve for a fixed n. There are better ways of computing this to make it more efficient, but this is like the bigger picture. Now, in practice, what you're going to have is you might get a location on the map x, y where you want to visit to deliver a food. And you're going to read the corresponding theta value from a pre-computed table. So this table could be computed by using the process which I just described in the previous slide. So this table is pre-computed. So every day when you get a new location, you're going to get the corresponding theta value. And you maintain 2 lists. So one list is just going to be a list in alphabetical order of all the locations you want to visit. So it's going to be a list of all your clients. And this list is going to be the more interesting part, where you sort the list by the theta values. And your driver is going to basically follow this order of visiting the places. And this is quite a simple process, right? It's very efficient. So if you look at the computational effort for you have to visit like n locations, then sorting is like the only big thing you're doing here. And it is sorting is very efficient. You're going to do in like order of n log n. And even memory wise, you're just going to have order of n memory register. You just have to maintain 2 lists. And basically the first list is just to have a database of what places you want to visit. But even more better, it's very easy to insert or delete new places here. So let's say if you want to add a new location, you get a new subscriber to this program, so you want to add their location as well here. You just get their location x, y, compute theta, and add that card in the corresponding order of the theta list and the alphabetical order list. Yes, question.
Transitions between each of the grid cells is kind of between the unit. Right? Because like with like your wheels on wheels path.
Yes.
That you consider the road length, and then like the road length is actually really far between.
Right. Yeah, but you can still map the entire. If you have a map, you can just map it to the unit square, right? You just have to do some kind of a transformation. No. You don't, there's no obstacles here. Yeah. Yes.
So that's what I'm saying, like, if you like say from like one location, you have to like go around. Then it's like, the road itself is like.
Right, but so you're assuming you have the information of the map, right? So a map basically gives you, if you're given two locations x, comma, y, and if you're given like a road map or something of that sort, something like similar to your Google Maps, then you know the distance on how you must go from x, comma, y to that point. So you're just scaling everything down to the unit square. Your map is basically a unit square.
The roads in the unit square, when we're transitioning from one square to another.
Right.
It's just showing some path in the XY coordinate, right?
Yes.
What he's saying is there might be a road there or there might not be a road there in the unit map when you are building a path. For example.
Right. Okay. I mean, considering like there might be like obstacles, so you can't like entirely. Yes.
The real world, there might not be a road along the path.
Right. So basically, this the map which you have is you're just going to consider. So if you don't have paths directly from here to here, you're just going to take the closest viable path. Any more questions in how this algorithm is like kind of implemented in practice? So this was actually implemented in 1982 in Atlanta, Georgia, where this non-profit organization Meals on Wheels used this as a routing technique for their drivers. So this data is from them, and you can see that the list changes kind of 14% every month. This is like data over a year for every month, and the number of people they are served keeps changing. So you can't afford to like keep recomputing, spend a lot of time recomputing this stuff. And this just cost like less than $50. So it was like very cheap. You're just maintaining two lists. You have some person to maintain this list. As you get a new subscription, or if somebody opts out of a subscription, you just add or remove the list remove their card from each of the list. But usually it's not a single driver doing their job. You're going to have multiple drivers whom you want to like spread across the route. So, and they did have some kind of a heuristic to partition the list so that approximately the size of each subgroup is equal. And so these are the actual numbers on how many meals they delivered. So approximately they delivered like 50 meals every day. And they took like 4 hours. So they start at 9 a.m. They finish at 1 p.m. to deliver all the lunch packages. And they travel to 35 locations, and they travel like 30 to 35 miles approximately. And they did this definitely shortened the average travel time by 13% compared to the previous method which they used. So this was like an actual thing. It was really practical. Any more questions? This right. So having talked about how this is really useful, I'm going to now dig into how this can be used as a tool to prove a very interesting theoretical result. I'll start from like the weak law of large numbers from a very simple experiment. Let's say you're flipping coin tosses. Each xi is a random variable which denotes the outcome of a coin toss. It could be a head or a tail. And I assign xi to be equal to 1 if it's a head and 0 if it is a tail. And you're just flipping these coins sequentially. And what the weak law says in layman terms is that the fraction of heads which you observe is approximately half, because the probability of being a head is half. So as n becomes really large, you're going to approximately see equal number of heads and tails. To be more precise, this is like the probabilistic statement. Sn denotes the number of heads which you observe, and Sn by n is like the fraction of heads which you observe, and that's going to be really close to the actual mean of each of the random variable, which is half. And this probability decreases exponentially fast with n. So this is basically the statement of the weak law. But what we are, if you look at it, this Sn by n is like a simple function of these random variables, right? It's just like summation of these random variables, and you're dividing by the number of coin flips. So what we want to think about is, can we say something a little bit more stronger? That is any function of these random variables approximately constant? Because here the argument you're making here is, this is some function of the random variables. This is kind of approximately close to a constant, it's close to half. But what if, can we make this kind of a statement for any function f, or some function f which you're interested in? And the function which you're interested in here is the length of the optimal route through the locations. I want you guys to think of x1 through xn as the locations on the map. And if these locations are kind of sampled according to some distribution, then can we say that the length of the optimal route is approximately constant? And we could definitely say that, because we can make some continuity arguments about f, and I'll go through in high level about some details on how we can make that argument. So sorry. So this is a very strong statement which I'm making, because if you can argue that the length of the optimal route for different locations on the map is close to some constant, then minimizing that constant would also give you some direction on how to minimize the length of the route. Yes, exactly. Yeah. And you're assuming this x's follows some kind of a distribution, right? Because most often than not, you won't have some locations which are really far away. So yes. I mean, for this analysis, we are assuming that, but you would want to incorporate some structure ideally. If you have to break some kind of independence if you want to. Yes.
Yeah.
No, so we are interested in looking at the optimal route, but maybe you could make some arguments about any route or something, because the direction which we are going here is we're going to use the Hilbert route as a tool to make this statement. But if you can make some connection between the Hilbert route and some other route which is not necessarily optimal, then we could also hope for this. You will see that this constant is basically going to depend on the distribution of this f, or in other words, the distribution of how you're computing the length of the route through these locations. So, but obviously we don't know how to compute the optimal route. So let's start with the Hilbert curve, which we just described. I'm going to argue here that this Hilbert curve is going to be continuous. We start with the observation that at stage n, there are 4 power n subintervals, each of size 4 power minus n, and each square has side 2 power minus n. And that is just an illustration for n equal to 1. And if you look at the construction again, if 2 intervals are adjacent, let's say 2 and 3, then their mappings are also going to be adjacent. In the sense that, so the subinterval 2 gets mapped to that square and 3 gets mapped to that square 3, and those 2 squares are adjacent. So you can already see some kind of continuity creeping in here. To make this statement more formal, the theorem is this mapping is in fact Lipschitz of order half, and 2 root 5 is exactly going to be a Lipschitz constant. The idea behind the proof is, if you have two intervals s comma t, you can basically make this statement saying that if you have 2 points in the interval s comma t, then they always satisfy this inequality for some n. If s and t are really close, you just increase your n. So as n tends to infinity, this is going to become 0. And if s and t are really far, you can make n equal to 0 so that mod of s minus t is less than or equal to 1. But this also means that s and t are in adjacent subintervals or they are in the same subinterval. Because the size of a subinterval is 4 power minus n, and this upper bound tells you that s and t will at most be in adjacent subintervals. But what it also means is that if they are in adjacent subintervals, they are in adjacent subsquares. And we can bound that distance as well. Let's say if 2 points are in the same subsquare, then the diagonal is the maximal distance between them. And you can compute the distance. If they are adjacent subsquares, then the diagonal of the rectangle is going to be the maximal distance, and you can still compute that. And that's where this upper bound comes in, so that you can make this Lipschitz argument. Now, having proved the Lipschitz of this mapping, we hope to prove a bound on the length of this route, which is computed via the Hilbert construction. Just some notation. Let's say xj are your locations on the 2D map, and theta j are their corresponding mappings on the unit interval, and theta parenthesis j is the sorted thetas. Now you can get the Hilbert space filling route just by sorting theta. So x by j are the locations on the 2D map in the order of the Hilbert curve. And the theorem here is the length of the Hilbert curve is bounded by a constant. I'm being a little bit imprecise here. By length, I mean not just the absolute length, but the sum of the squares of the distances between adjacent locations. And the proof is basically exploiting the Lipschitz continuity of FH. So this summation is going to be the length of the Hilbert route. And then so you can apply Lipschitz to each of these terms in the sum, the Lipschitz continuity argument in the previous theorem. You will get a telescopic summation if you expand out this sum. Then since you're mapping it to the unit interval, the maximal distance is going to be 1. And that's why you're able to make this upper one an absolute constant. Yes. Here you're just bounding the sum of the squares for distances, right? It's not like the actual length. I'm just ignoring this fact. That's what I mean. I'm ignoring this. Yeah, that's square. Yeah. Yes. Any question? Right. So having bounded this length of the Hilbert route, we hope to bound the length of the optimal route as well using this. And the idea behind this is, let's say you have a set of locations X, and you are able to compute the Hilbert route for these set of locations. Just for analysis, let's say you also have access to the optimal route for another set of locations Y. I construct a new set of locations Z, which is just X union Y, and I construct a route for Z. So the best I can do for Z is I follow the optimal route for Y as long as I move through the locations in Y. And when I want to visit the locations in X, I use the Hilbert route for X, because you don't have the optimal route for X. The best you can do is just follow the Hilbert route for X. So for example, The black dots, capital A, capital B, capital C, belong to both X and Y. The gray dots here, they belong only to Y. Yes. Capital A is location in X and Y. Yeah. Yes.
Is it possible to visit the locations in X multiple times? Like if you were to do space filling route in every
No.
location.
The space filling route for X is not going to visit the locations more than once. But the route in X, Z is not a space filling route, right? Because when you have the optimal route for Y, just follow the optimal route for Y.
Visit other locations in X.
You are visiting. So if you look at the route for X, let's say you start from A, you're just going to go clockwise and visit all this. So you're not visiting. You do visit all this, but you're not visiting anything more than once. So if you, let's say you start from the small a in Z, you're going to follow the optimal route for Y, which is A, B, E. Now you have to visit V somehow, right? And from E, you take the space filling route, which you already computed for X to V, and you repeat the process. You come back to E, follow the optimal route for Y, and then again do the space filling route for X. Sorry? Why not go directly? Because you still have to visit S, right? Otherwise, you will miss S on the way. So Z is going to have X union Y, so you have to visit S somehow. So S is here.
No, so we reach the one.
Oh, you could, but the space filling route which I computed for X is like clockwise. So you're going, the space filling route which you have access to is this route which goes from E to V, but not from V to E. You could have like a counterclockwise direction also, but that is still going to translate to Z, right? Instead of going from E to V, you will go from V to E. Right.
Still following your clockwise pattern. Like why do you visit?
Why can't you visit from V to C? Because that's the route which you have access to. So C is only there in Y, and V is only there in X. No, you might have a route, but you don't know how to go from V to C. The only way to go is from V to E to C, which you have access to. Like you have access only to this optimal route for Y and the Hilbert route for X, and what's the best you can do with it? So the length of the route for Z is going to be the length of the optimal route for Y plus these extra leaves, right? And these extra leaves correspond to the length of the Hilbert route for X. It's not exactly equal to the length of the Hilbert route, but some constant times the length of the Hilbert route. Yes, so what I mean by a space filling route is exactly the route which I showed in the beginning, the space filling route. And you are interested in finding or bounding the optimal route for X. Since Z has more locations than X, definitely the optimal route for X is going to be less than or equal to that of Z. In fact, even more is going to be less than or equal to the specific route which we constructed. So L of X is the optimal route for X, and you can bound that by the route which we constructed for Z. And the length of the route for Z is going to be the length of the optimal route for Y, plus some constant times the space filling route for X, because those correspond to the extra leaves which you saw. And since this, we prove that a space filling route is bounded by an absolute constant, we can make this statement. We use that here. And I'm going to skip a lot of details here. But from here, you can basically prove this concentration type of inequality, which says that, okay, let's say the set of locations in X is follows some probability distribution. Then this event is going to occur with high probability. So the M is the median of the length of X. You could hope to somehow get this M through L of Y in the analysis part. And the more interesting fact here is the decreasing rate, the upper bound is independent of the number of city locations. So whatever number of city locations you have, the length of the optimal route is going to be very close to the median. Yes. Because usually in the weak law, we make statements saying that the function is close to the mean, right? Or the sum of values is close to the mean. Here, you might not have access to the mean of the length of this route. The length is another random variable, and it's like some kind of a complex function of the random variables x1 through xn. But you always have access to the median. So median is basically defined as approximately the middle part of your. So L of x is a scalar, and the probability that L of x is less than or equal to m is approximately equal to probability L of x is greater than or equal to m.
I don't understand why like the median is easier to compute.
No, it's not easier to compute, but the mean might not exist for certain distributions.
So for this distribution,
no, we don't know whether it exists or not, but it might not exist. But median always exists. Yes.
because it seems like you cared about the mean instead. If you know that this function L is Lipschitz, then you can just apply an isotropic inequality to get this exact result.
For the mean. Right. Okay. I'm not sure about that. Maybe it is possible, but yeah. The argument which they use is the mean might not exist for all distributions, so they're making some they're making this statement for the median.
Okay, because you told us like about this sort of, we started with like really red variable. Right?
Yes.
And you argued that by the weak law, I'm going to concentrate on.
Yes.
But here now we for like some reason
Switch to the median. Yeah.
So that's,
Right. Okay.
whereas I think if you stuck with the mean, then
You could make a
it
more. Right. Okay. Yeah. Sure. Yes. Yes, but I think you have to use like some kind of different technique to guarantee that the mean exists, and yes.
It would have some connection with the fact that the optimal length for any set of locations was approximately constant. Earlier saw that that has some connection to the
So in the analysis part, the median is coming from the fact that if you just look at a set of locations y, or the optimal route for y is less than or equal to some number m, that m is basically being your median there. If you have the mean in that case, yes, maybe if you use some different technique, you can say that with high probability. But you could definitely make some argument about the median using the analysis which was used here. I can definitely like point you on how the median creeps. Yes.
I understand the importance of this failing out in the analysis. I'll tell you why. So at first I choose an order with the two displays, right?
Yes.
And then I start and draw samples from these two displays, which are only my model decided according to some distribution.
Right.
So, am might be wrong, but this space filling out
Mhm.
is only dependent on the parameters of the distribution, right? And the order. So why is this informative? Why is it informative to say that,
Mm.
okay, if I go and draw some points at random and I want to visit these points,
Mhm.
but not from some that I decided,
Mhm.
this will give me some intuition on how to perform the optimal.
Right, yeah. It is when you're going forward to bound the length of the optimal route, it is definitely very unintuitive on how this comes in. But somebody just discovered that, okay, this could be useful, but only because of this space filling route, you are able to make this bound. That's why this is useful. You're using this as a tool to bound the length of the optimal route for any set of locations, using the space filling route for those same set of locations. Because the space filling route is somehow nice.
It's just like an algorithm that you compare.
Yes.
And factorial.
Yeah.
Do this. Like do this sort.
Yes.
But we don't know what this is supposed to.
Yeah, we don't know. But actually, there is a statement in the paper which they wrote saying that the ratio of the length of the Hilbert route and the optimal route is asymptotically close to order of log n, where n is the set of locations. I haven't looked through the proof of that, but this was like a theorem in the paper which we. So this is basically what we were after, right? The length of the optimal route is essentially constant. We are able to prove some kind of a concentration inequality on this complicated function L. I think that's all I have for today. Do you have any more questions? Okay.
If you're in the back, if you're not one, you're pretty crowded.
Hi, how's it going?
I just want to